too many videos is too much trouble.
Yeah. Okay, so we just came back from, we added a simple add and contains. It works as long as you have one node. That's kind of not a very good data structure, but we've talked about a binary tree and how it's actually going to add the nodes. So, question here is how are we going to add these nodes? Well, let's go jump over here and let's see if it talk about traversal in a minute. Maybe? Oh, it talks about insert? Wow, that's complicated. All right, well that's useless. Wait, is that delete? Okay, think slides. You have failed me yet again. All right, what do we have? We have root pointing to a 0. I'm drawing on the board for people online. Okay, and now we want to add, is marker not working? There we go, add. That's gonna look funny. Oh well.
I expect nothing less.
Nothing less. Good. All right. Where does this guy go?
We're probably going to add it to the right?
Yeah, so we take roots and we want to add the one here. All right. Let's do a couple more examples. I'm going to add, this time I'm going to add 5. Where does it go?
To the right of the 1.
To the right of the 1. I'm now going to add 3. Where does it go?
To the left of 5.
To the left of the 5. All right. And sure. Let's add 10.
Right of the 5.
Right of 5. And then one more for emphasis. I'm going to add 4. Right of 3. Someone say something else?
Or left of 10.
I can't go to the left of 10 because it has to.
Yeah.
Yep, so it has to be to the right of 3. Okay. Well then, that's interesting. How are we going to go about adding? Might be helpful to think about how are we going to add the 4. Let's look at adding the 4. Did they get rid of my erasers too?
We stole everything.
Does this work? Good. And it does work eventually. All right, we're going to add the 4. Okay, if we're going to add the 4, what's the first thing we need to do?
I guess go through the tree.
Go through the tree until
You find the correct spot.
and that correct spot is defined by which one?
An empty node.
An empty node. Well, not just any node. Well, it can't be empty actually. So first off, there's this check of if is the tree empty. If it's empty, we add it to the top. So that's actually a pretty good check. After that, we know that the tree is not empty, which means we need to find the parent of where this guy needs to go, right? Either to the right or to the left. Okay, so that means we need to traverse the tree until we get to a location. There are different ways to do this. Sure, I'll call it a rover. Why not? We have rover. Well, I would start at the root. What's that?
We love Rover.
We love rover. All right. Rover is looking at 0. And notice, or looking at the root node, can 4 be a child of the root node? No, a direct child, not a grandchild, a child.
No.
No. Sure, it'll be an offspring, but it can't be. Why is that? Because it's not less than 0, so it has to go to the right, but that's occupied by a 1. So we're going to move rover to the right. That doesn't work too bad. All right. Now what do we do? Go. I couldn't hear you. Sorry.
Do we just check the one?
Check the 1. Can it be one of the? Can 4 be a direct child of 1?
No.
No. Can't go to the left because it's 4 is greater. If you go to the right, there's already something occupying it. So we're going to move rover over to the right. All right. Now we're at 5. What do we do next?
I suppose we evaluate it.
Yeah. So we're evaluating the value against its current value. Is it greater than or less than?
Less than?
Less than. So we're going to look to the left. Is there a node there?
Yes.
So now we need to go to that node. Okay. So now we're here at the 3. Is it greater than or less than 3?
Greater.
Greater than? Is there anything to the right of 3? No, so we can put it there. Notice rover is going effectively to the parent of where it needs to be, of the parent of the new node. So then we know once we're at the parent, we put the 4 right there, and we're good to go. Okay. Great. How do you want to do this?
With an if statement?
Whew.
You first give this thing, insert mode, right?
Yeah, okay.
Well, I'll need that.
Either one. They're actually the same thing.
Mm.
And then return true inside that if statement. So that we can, yeah, that way we break out of it. So that's the sanity check. Great. All right, now what do we want to do? Dash val. Or arrow val. Oh, for loop, you probably want rover to start at root.
Yeah.
Yeah. Ooh, you may want to do a while loop because there is no, I mean the incrementation or the incrementer is going to be an if statement because you're going left or right, so it may be clear if we use a while. You need to declare rover right before the while.
Yep.
Yeah. Root. Yeah, linked lists like to have heads, trees like to have roots. And yeah, now we're checking against rover and not root. So yeah. All right. Right. The if statement should be of rover. Right, aren't we comparing? Because we're iterating through rover. Yeah.
Oh.
Yeah. All right. That'll eventually get, well, there's a kind of an error here. I'm going to go ahead and help fix this. Because you either want it to go to the right or to the left. You didn't want it to go to the right first and then all of a sudden go to the left, right? And also to help clear this up even more, this statement is actually superfluous. Okay, we're doing this, that's fine. Actually, which way do you do it? Do you do it this way? I've seen so many different ways. And I've also seen this. Like, I don't care. Whatever. I don't know which way you're doing it. But anyways. Okay, sure. All right, so if it's less than, you go to the right. Otherwise, you're going to the left. Good. Well, that gets rover to the end. If you think about that, rover is going to go all the way until it's null. So it's going to go one farther than we want to. If you look at the board, it's going to go boom, 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 boom. This is still a valid node, so it's going to go to the right and then be equal to null. And we don't want that. We want rover to be equal to the parent, so we know where to add the node.
It's a pain.
So what there's different ways to do it. The simplest way I would tell you is just put it right here. So if the right is null, what do we do?
Add it.
All right, do it. And you had it. Rover dash right. Well, I've already created the node, and it's null null, which is good. And then let's go ahead and return so we can break out of this loop because we've finished it. We are returning true in this case. All right. And now we effectively need to do the same thing for going the other direction. Okay. All right. Let's see if that works. Ooh, fail. Line 30. I think we're failing the contains, aren't we? Oh, we got the first one correct, but not this one. Well, good. What's really going on is contains only evaluates the root. All right. I want to show you all something real quick. Let's see. So what we're going to do here is instead of this code, I'm going to comment it out. I'm just going to return contains rec, passing in the root node and the value. What I'm going to do here is if node is null, I'm going to return false. If node val equals val, return true. So those are the stopping, but we want to check if it contains it, and this is a recursive call. So it's going to, this is where we're going to start to recurse. So the question here is, well, if node.val is less than val, then we want to return contains rec of, well, which way are we going? So if val is greater than it,
To the right.
we want to go to the right. So we'll go node right, passing also val. And then for the other direction, well, actually, we don't need to do an if statement here. Just return going to the left. Y'all see what happened?
Mm-hmm.
All right, let's see if that works though. Oh, wow, first try. Nice. All right. Okay. So that's the recursive contains. It's just recursing down the tree, trying to find where it is. Okay. Now, what's that?
There was one more thing after that, right?
Oh, there's more. Oh man, we're cruising through. That's great.
Yeah, it was like we're going.
No, there's a couple more, and then we're going to be done. But it's not too much. Right now, before I continue on, I wanted to point out something. This, of course, is recursive, and this up here is iterative. We could have done the iterative version, which is basically from here to here inside of contains, or we can do the recursive version. And you know what? I will go ahead and write the iterative version for emphasis, so we can at least compare the two. Oops, I almost did it again. Et node rover equals root, while rover, and then I'm going to go if rover dash val equals val, return true. If rover dash val is less than val, rover equals rover dash right, else rover equals rover dash left. Make sure I did that right. That's correct. And at the end we'll return false. All right, let's see if I did that correctly. Oh, good. So there's two versions. Which do y'all prefer?
Recursive.
Recursive? Anyone for the iterative one? You are? All right, no, that's fine. That's fine. For a binary tree, there's a lot of situations where just looking at it recursively is going to be a lot easier. So, and I'm not saying the iterative ones, because the iterative solution to this is not that, it's not really that bad. I mean, it looks a little more crazy, but it's not really that much worse. It's really not. But I'm just for all of you that are for the iterative one, for the binary tree, if the iterative one's giving you problems, stop, think recursively, because there's situations, a lot of situations, where the recursive solution is extremely simple compared to the iterative one for a binary tree. All right. So I'm going to go ahead and comment this out and go back to the recursive solution. Jump back here just to make sure. Good. Excellent. All right. So we could have also done the recursive contains or add. In which case, when you add, it's basically this right here. You do this check up here first, and then you do a check that if it's less than, then you do an internal check of saying, can we add it? If so, do it. If not, recursive call is what it comes down to. All right. Any questions on adding contains? It should be in the HPP file. I think it is. Yeah, it's right here.
But contains rec.
No, it's a private function of this file.
Yeah, it doesn't
Oh.
have the, yeah.
And that's fine. That's only fine because notice I'm passing in the BT node and the value, so it's not having to access anything from the class. So that's why this is okay.
Okay.
All right. If you're going to access any private memory variables or whatnot, it would have to be part of the class, but it doesn't have to be in this situation. All right. Good question.